Today, it's our pleasure to host Nouamane Tazi from Hugging Face. He's the lead author of the Ultrascale Playbook and a core developer of Nanotron, Hugging Face's open-source distributed training library. His work spans projects like StarCoder 2, Small LM3, and Mixture of Expert Scaling, with several initiatives, and he is passionate about making large-scale training practical and accessible. So without further ado, let me hand it off to him.
Thank you so much for the invitation. So, hello everyone. My name is Nouamane Tazi. I've been working with Hugging Face now for 4 years. And the talk for today is scaling training to thousands of GPUs. So today's talk is going to be mainly inspired by the book that Hugging Face made. It's called the Ultrascale Playbook, so make sure to check it out. It's available online, and there's a printed version if you need it. But I also added some elements since the book now dates from 1 year ago, especially regarding MOE scaling and some new things that we can take a look at. So without further ado, let's start with the first question is why does scaling matter? And if we take a look at the latest releases of the latest LLMs, we can see that the trend is still to train larger and larger. And why is that? That's also because we can see that there's a correlation with intelligence. It seems that the more, the bigger the LLMs are, the smarter they are. And there's just an example from this week, Kimi K 2.6, which is also a 1 trillion parameter model. So to take just some numbers, models of these days are 1 trillion parameter large or even larger. They get trained on 15 trillion training tokens, and for context lengths as far as 1 million. So how can we do that? And to take some quick overview about what does this entail from a infra point of view. So if you want to train this kind of model, first you need to load the data, which is like about 15 trillion. Imagine that's stored on a storage somewhere, and you need to load that continuously in your training loop. And each training iteration, even if the model is as big as 1 trillion parameter model, needs to take about 1 second. And you're limited by the memory within each GPU or TPU or whatever you're using. And you need to save checkpoints to that storage every now and then. So you're putting a lot of pressure into these GPUs. So the talk of today is going to be mainly focused on training, the training iteration or the training. So let's start quickly on one GPU. So there is a model. We do forward, backward. We compute gradients, and then we do the optimizer step, and we have an updated model. But for our case, we usually have global batch size of 1 million to 10 million, even like 50 million tokens. So that, of course, doesn't fit on a single training iteration. So what we do usually is we can do gradient accumulation. So we're going to divide this batch size to smaller batch sizes, and we're going to do multiple forward and backwards, and we're going to accumulate gradient sequentially. The problem with this approach is we're going to assume that the model already fits in memory, which is not always the case. Models now are so big, 1 trillion, and we said that we're still limited by the available VRAM in each accelerator you're going to use. So how can we solve this with more GPUs? The other thing is that if you train sequentially with this approach, you're going to need to wait for a long time. So if we have more GPUs, how can we speed this up? And for this, there is multiple forms of parallelisms we can use. And each one of them is used in a specific use case. And hopefully today, you can get at least an intuition which parallelism you can use for which use case. And to help you, so basically for today, I'm going to mainly focus on the first two parallelisms because they're going to explain just the intuition of how we can think about these parallelisms. And the final three, we're going to just quickly skim over them because there's not enough time. And I think that the approach can be generalized. So before starting, quick few notes. So this approach can be applied to an accelerator, GPUs, CPUs. So in the slides, I use GPUs, but the same can be applied for anything. And it's useful for pre-training, post-training, distillation training, inference. So any type of workload can benefit from these parallelisms. And it's applicable. You don't need 1,000 GPUs to benefit from this. As long as you have 2 at least, you can benefit from these parallelisms. So naively, what we want to do, so we said that the model doesn't fit. So ideally, we want to be able to shard the model, so either vertically or horizontally. And that means we're going to also shard the gradients and the optimizer, and shard the data, because we don't want to wait too long for to train sequentially on data. So let's deep dive into scaling. And first of all, we're going to start with data parallelism. And I'm assuming this is the basic form that everyone is using. So I'm going to go quickly over it. So instead of training sequentially over multiple batches, I'm going to feed each batch to a GPU. So I'm going to have different batches per GPU. That's the name data parallelism. I'm going to shard the data. And of course, if I have different data per GPU, each GPU is going to compute different gradients. And to keep the same model duplicated on each GPU, I'm going to need to synchronize these gradients. And how am I going to do that? It's going to be the same as accumulating gradient, but it's going to be in a distributed fashion. Thus, we're going to need to use the all-reduce collective operation, which is just a distributed sum over multiple GPUs. So we end up with the same gradients, and thus we can do the same optimizer step over all GPUs. And if we want to take a look at the code, it's going to look like this. We can use the DDP class by PyTorch. And when you wrap your model with it, when you do the forward and backward, it automatically handles the all-reduce part in the backward. So there is a small problem with this is when we do the all-reduce, do the GPUs stay idle in that time? And for that, there is a very nice tool called Torch Profiler that helps you visualize what the timelines, basically, or the workflow for the CPU and GPU. And for example, if we apply it on a naive implementation of DDP, we can see that there is the CPU stream, there is forward and backward, and then there is the GPU streams, GPU computation and communication. So there is two things. So the biggest thing that we want is we don't want GPU to stay idle. So we definitely want the GPU computation stream to be always full, which is not the case in here, as we can see here. The other thing is we need to make sure that the CPU is always ahead of the GPU so that we can always schedule kernels beforehand. And the third thing is, for example, in this case of DDP, we can see that the all-reduce is not overlapped with the computation. So ideally, we want to overlap this communication with computation. So this is a simplified diagram of the previous. So how can we overlap this all-reduce? We can just start all-reducing the gradient once a bucket of the gradients is computed. Basically, when you do the forward, you start doing the backward from the last layers. So you don't need to do the backward of the entire model to be able to all-reduce them, right? So once, for example, you compute the gradients of the last layer, you can already start the all-reduce. And this is what we do in practice. So for example, if 2 is the last layer, once the gradients of the last layer is computed, we can all-reduce it, and we can continue doing the backward. And this bucket, we can control the size of this bucket in PyTorch via this argument, bucket cap microbytes. So you can control how big or how small the buckets should be so that you have a better overlap of communication and computation. And this is what goes through the mind of any engineer who tries to scale models. Basically, when you have a lot of GPUs, you definitely want to overlap efficiently your computation with communication so that you avoid any idle time here for the GPU computation and to benefit of the tensor cores of the GPUs. So this is the end goal of this presentation. So quickly, we can go over a recap of DP. So it's easy to implement. It's very efficiently overlapped. It's really good. And it's model agnostic, right? So we can just wrap any model, and it's going to automatically reduce the gradients in the backward. But the problem is that the optimizer step is duplicated across GPUs, right? Because if you have the same model in each of your GPU, all of them are going to do the same optimizer step, which is bad, right? It's duplicated work. The second thing is that if you scale more and more in the number of GPUs, you're also going to need more and more batches of data. And this is what we call global batch size. So your global batch size is also going to scale. And of course, you can't just scale indefinitely, right? We're limited by tens of millions of tokens. And so you can't just apply DP. If you have, I don't know, 1 million GPUs, you can just use the DP over all of your GPUs. And the third thing, which is the biggest bottleneck, is that DP assumes that the training step fits in memory. And this is not always the case, unfortunately. And so we need other approaches to optimize memory. And we can look at the first one, which is DP0. So from the name, DP01 tries to solve the optimizer step. Basically, we said that in DP, we're going to duplicate the model, and all of them are going to do the same optimizer step. So how can we reduce the memory, at least of the optimizer states, so that they're not duplicated, and each GPU can do a different part of the optimization? So the simplest approach is instead of having the optimizer states of all the models, I'm going to shard them across my GPUs. And when I do the backward step, I'm only going to scatter the gradients. So I'm not going to have all reduce here. I'm only going to have reduce scatter. And then I'm going to do the optimizer step for each shard. And this is what's really good about 0.1. We're not going to have duplicated work. And once I have my updated parameter shards, I need to all gather them before the next step. So this is 0.1 in brief. And there is a very important intuition that you can learn from this. So before in vanilla DP, we had an all reduce in the backward, right? In here, we had an all reduce. And the trick that we made for 0.1 to work is that we replaced the all reduce with a reduce scatter and an all gather. And this works great, and we're going to reuse this trick in the future. Why? Because all reduce essentially is just a reduce scatter plus an all gather. So basically, we didn't add any communication. Like, it's the same communication, it's just that instead of doing the all reduce, I did the reduce scatter first, so that to compute the gradients first, and then I can do the optimizer step, and then I all gather the parameters. The second thing is, for the gradients, I didn't use all of them, right? So when I did the reduce scatter, I only used the shards that I optimized later. So I can just throw the parts that I don't need from the gradients, and this is 0.2. So 0.2 optimizes or saves memory even further by just discarding the gradients that I don't use. And this is the difference between 0.1 and 0.2. It's a small difference. It's just that I don't need to keep the gradients. So it's easier said than done, right? Because in the implementation, it's annoying to just discard things. So people usually just use 0.1 and they keep the gradients. And also an important note, since now there is Muon optimizer, optimizer requires the full tensor's grads. So previously, people would take their entire parameters and they would just shard them. They would flatten everything. So we don't keep the notion of a tensor, right? You just flatten all your parameters, and then you would shard them along the number of GPUs you have. But the problem is for Muon, you can just split your parameters, right? You want your tensors to be full so that you can do the Newton-Schulz optimization on them. So the thing is here, when you want to split your parameters or your gradients on your GPUs, you need to make sure that to keep your tensors full. So for example, I'm gonna give the first, I don't know, 5 full tensors to the first GPU, and the second 5 tensors to the second GPU. Yeah, so this is for Muon, but also for other optimizers. And lastly, for 03, I also want to save memory of the parameters. And this is the craziest part, because how can I save memory by sharding the model's memory when I need them in the forward and the backward? And there is a very nice trick that the 03 engineers came with, is when I do the optimizer step, I don't need to all gather right away, right? I can just keep the shards of the model on each GPU, and whenever I need to do the forward of that layer, for example, for the first layer, I'm just gonna ask for these other shards from the other GPUs. So for example, for the first layer, I'm gonna ask for the other shards, I'm gonna do the forward, and then I'm gonna free the other parameters. And then for the other layer, I'm gonna do the same thing. So this looks very slow, right? Because on each layer, you need to ask for all for the rest of your parameters from your other GPUs, do the forward, and then free them. But in practice, it works very well. And the reason is, by the way, it's the same for the backward. So for the backward, we also just do the all gather of the weights and then compute the backward, and we free the weights. So the reason is we prefetch the next layer while computing the current layer. So this is the trick. So I had previously an all gather here, right, after the optimizer step. But now I just separated the all gather on multiple layers. And for example, for the first layer, I'm gonna all gather it here. I'm gonna do the compute. And while I'm computing the forward of the first layer, I'm already all gathering the next layer, etc. And then I free it, etc. And so concretely, I never have more than 2 what we call FSDP modules or FSDP units in my memory, because I always free one when I all gather the other one. And the same thing for the backward. And so I still do the distributed optimizer, and I repeat. So this is basically the best form of DP that we can have. Why? Because I efficiently optimize my memory. I saved memory on optimizer states, on gradients, and on the model. And I also prefetch, so everything is very well overlapped. And besides that, similar to DP's bucket size, I can also control the size of the buckets, which we call the size of the FSDP modules that we have. And so for the code, so there is 2, by the way, 03 is also called FSDP. FSDP is fully sharded data parallel. And there is 2 versions in PyTorch. So FSDP1, we used to just have a class, FSDP, where we can wrap our model, and we can define the wrap policy, which is similar to the bucket size. And for FSDP2, there's now a function called fully shard, and you just call it over your model, and it's going to automatically transform your modules to FSDP modules. So the difference between the 2 versions, the first one, as I said, it flattens all of your parameters, and we already talked of the problems of that. For example, Muon and some optimizers, they need full tensors, and this is bad. So ideally, when you shard your parameters, you want to keep full tensors on each GPU. So FSDP2 enables that. The second thing is FSDP2 uses dtensor, which is a new utility in PyTorch, and it helps it being combined with other forms of parallelism, as we're going to see. And so to recap, let's compare 02 with 03. So in 0.2, we had a big all gather here to all gather the parameters that we optimized. And in 0.3, I just divided this big all gather into smaller all gathers of the different FSDP modules. So it allows me to overlap this all gather with the forwards, and I can control the size of the FSDP modules. And it's also model agnostic because I don't care about the architecture of my model. And it's just great. It works very good. So the pros and cons of DP03, it trades memory for comms, right? So DP vanilla, I didn't optimize memory at all. I just assumed that the model fits in memory. But if I needed to save memory, I can just do 0.1 or 0.3 or 0.2 or 0.3. And this is something to pay attention to. So a lot of people just throw FSDP2 on all of their models. And this is not a good thing. Because if your model fits on GPUs with 0.1, you don't need 0.3, right? Because 0.3, just you're going to add more communications and you're going to make your training slower. So just use the 0 degree that you need to save memory, because there is no other benefits. Like if 0.1 fits, it's going to be faster than 0.3. So the second thing is the great overlap of comms with compute. As we've seen, everything is well overlapped. And the third thing is model agnostic. So there is no headache of implementation. You can just, whatever the PyTorch module is, you can just wrap it with FSDP. You don't care if it's a state model. You don't care if it's anything. It's going to work out of the box. The negatives, though, is that at scale, since you need to all gather and the parameters for each FSDP module, if you scale it too much, even if it's overlapped, you can't hide the communication anymore, right? Because it's not perfect. If you have very slow network, you cannot overlap that anymore. So there is a solution for that, which is called hybrid sharding, or HSDP. So you would use FSDP on a smaller circle, and on the larger circle, you can use vanilla DP. So this is something you can look up later. And the other thing is 0.3 is we're still in data parallel. So we're still scaling with batches. So every GPU has a different batch, and we still have this restriction. We can't scale indefinitely. So what if I reached my global batch size? So I have, I don't know, 10,000 GPUs, and at 1,000 GPUs, I already reached my global batch size. I need another form of parallelism. So let's take a look at TP. And the motivation behind tensor parallelism is that if I have a model, transformer model, for example, I want to keep the same batch, so the same inputs, the same data, and shard the model so that I do the same computation as if I had one GPU. So basically, instead of doing the computation with one GPU, I would do it with two. And essentially, I'm going to shard the memory for my model, for my gradients, optimizer states, by the number of GPUs I have. So the question is, and this is a very fun question that people like to ask in interviews, etc. So do we keep full or half activations in tensor parallel? And we're going to answer that after a bit. So let's start with an easy example, which is matrix multiplication. So if we take x multiplied by w here, a simple approach, and we want to parallelize that on two GPUs. We can just split our matrix on columns, and then I can all gather the outputs. Let's take the example of two matmults now. So I have y1, which is x multiplied by w1, and y2, which is y2 multiplied by w2. So if I split my first weight by columns, and if I split the second one by rows, I can do the same computation, which is two multiplications, and then I do an all reduce here. And I would get the same result and the same computation as if I did this with one GPU. So this is kind of the power of tensor parallelism, and this is the intuition behind it. If I had one GPU, I would do 2 matrix multiplication with the full matrices. So I managed to distribute this operation on 2 GPUs by splitting the weights. So each GPU only has half the weights, and each GPU only does half the compute. But the caveat of this is that I need to do a distributed communication, an all reduce, to keep the correctness. How does this work for the backward, though? It's the same thing. And again, I'm going to assume that I have the same upstream grad. And this is a big headache. We can talk about it in a bit. So if we assume that I have the same upstream grad, which is this, dy2 and dy2, similarly, it's just going to be multiplied by the transpose of w2 and w1. This is, of course, to compute dx, which is the out gradient. So again, it's just, I'm going to do 2 multiplication. And again, it's just half the weights. And again, I just need to do an all reduce. So to efficiently distribute 2 matrix multiplications on multiple GPUs, I'm going to need 1 all reduce in the forward and 1 all reduce in the backward, under the assumption that I have the same upstream gradients, which is the outputs, and I had the same inputs. So let's apply this on our MLP. So in MLP, we have, for example, activation of x times a, and then I multiply it by another matrix. So I always going to have 2 matrix multiplications. So I apply the same trick. The first one is going to be a column linear. The second one is a row linear. And I need an all reduce to keep the math correct. And as we said, we assume, and this is a big assumption, in our transformer, we assume that I'm going to always have the same activations, the same inputs, the same data. And I need to have the same outputs and later the same upstream gradients. So all the operations after Z must be the same in the 2 GPUs. And another thing to basically what we said, we're going to divide the compute by half. So A1 and A2 are halves of the original matrix A, right? So hidden dim is sharded in here. And this is what we just said. We needed the same input, and we needed the same upstream gradient to keep the math correct. Let's take an example of attention. So for attention, similarly, we have 2 matrix multiplication, which is the QKV projections and the output projections. So the question would be, should we shard along hidden dimension or number of heads or both? And what does it mean? So the question you really want to ask, and this is a very generic question, if you have a model and you don't know how to implement tensor parallelism on it, or you want to check that the implementation is correct, you should really ask, would GPUs compute the same activations as without TP? So let's say I sharded along head dimension, right? Then when I do the softmax, which is Q times K, it's going to have a reduced hidden dimension, and that would impact the softmax calculation. So it wouldn't give the same results as if I had TP1. But if I sharded along a number of heads, since the heads are independent, I would get the same activations as if I didn't use TP. So this is really the whole thing. So we shard along number of heads since the attention heads are independent to keep attention correct. And again, we need the same inputs and we need the same upstream gradients. So as a recap, the pros is that we shard the model and compute across GPUs, and we're memory and sample efficient. So at the same time, I sharded memory, so model parameters, gradients, and optimizer states. And I didn't need to have multiple batches, right? So I used the same sample across my GPUs. The second thing, I didn't need an all-reduce for the gradients, because all GPUs, I'm assuming they're doing the same work. It's like I have one big GPU that I distributed on smaller GPUs. And the cause is that communication is heavy, because at each attention, at each MLP block, I need to do an all-reduce for the forward and for the backward. The second thing is, and this is something we can see later, the parameters that are outside the TP region, which is the region where the hidden dimension is sharded, should stay synchronized. Otherwise, I won't have the same inputs and the same upstream gradients, right? Because this is a big assumption for the matmols to stay correct. So in practice, the parameters that are outside the TP region, they need to stay the same. They need to stay duplicated. So in practice, we all reduce their grads. And this is something that screws up training when you use TP. And just due to numerical precision, because theoretically, you don't need to do this. But due to numerical imprecisions, they drift apart. So in practice, we all reduce their grads. And the third thing is, of course, complex implementation. And it's not easy if you change the architecture. Let's say you want to use MLA or some other fancy attention. It's a headache to apply tensor parallelism on it. So let's take a look at sequence parallelism. So what's the motivation behind sequence parallelism, which is a flavor to TP? So in TP, we've seen that we have this TP region, which is the attention, and this TP region, which is the MLP. And we do the all reduce here. So the second layers, which are the row layers, they have an all reduce. Okay, cool. So in the TP region, the shape is sequence batch, and we shard the hidden dimension, we said. And after the second matrix in each TP region, I'm going to get back the original shapes. So I'm going to get back the original hidden dimension. So the question is, these parts are duplicated across GPUs. And it's annoying, as we said, to keep them synchronized. As we said, in practice, we need to all reduce this layer norm. And if I had some other operation, I also need to make sure it's replicated. So can we just distribute them as well? And this is what sequence parallelism tries to solve. And we're going to use the trick that we talked about earlier. So we have an all reduce. And we know that all reduce is reduce scatter and all gather. So how can we apply it in this case? This is what sequence parallelism is. So this all reduce, I'm gonna replace it with a reduce scatter. And I'm gonna, this identity, can call this an identity. This identity, I'm gonna transform it to all gather. So in the TP region, I'm gonna shard my activations along the hidden dimension. And then I reduce scatter along the sequence dimension. So in this sequence region, SP region, I have my sequence, which is sharded by TP. And then I all gather it again to have H, which is sharded. So basically, I play between sharding along the hidden dimension and along the sequence dimension. So this is moving from TP to TP with SP. And what this helps me do is multiple things. So first of all, the activations that are stored. So before I had to store very big activations here, which are SBH. But thanks to sequence parallelism, my size is always divided by TP. So this helps me avoid big activations. The second thing is it's the same amount of communications. Since all reduce, as we've seen, it's just reduce, scatter, and all gather. So I didn't have to add any communication. And the last question is about layer norm. So since we did this operation, should we sync layer norms grids in this case? And the answer is no. And for this, let's take a look at the backward. So similarly to what we did before with the matmoles, you can verify later that the backward of a reduced scatter is all gather, and the backward of an all gather is reduced scatter. Basically, reduced scatter and all gather, they are inverse of each other. So if this is the forward, the backward becomes like this. So the backwards, I'm gonna do all gather here, and then reduce scatter here, etc. So we notice here that before layer norms, we have reduced scatter. And thanks to these reduced scatter that I now added, they take care of synchronizing the gradients. So it's really beautiful that it works out like this. So thanks to the fact that now the GPUs, they don't do the same work, they see different batches. And thanks to the fact that in the backward, I have a reduced scatter here now, instead of just assuming the perfect case that it's an identity and that the layer norm would always stay synchronized. I just have this all gather and the reduced scatter, and they take care of synchronizing my gradients. So you can verify this, the inverse of reduced scatter and all gather later. And the pros cons, so let's take a recap. So the pros is that now we're sharding the model and compute across GPUs, and we'll be in memory and sample efficient, especially sample efficient, which is what we didn't have in DP. And again, we don't need grad all reduce, because GPUs are essentially doing the same work. And thanks to SP, I don't need to all reduce layer norms as well, because they now have the reduced scatter in the backward. But we still have the same problem. We're communication heavy, and the implementation is complex. And for this communication heavy, this is why it's recommended, if you've taken a look at the different distributed training libraries, they recommend that you use TP within a single node. So if you have a node of 8 GPUs, they say that it's better to use TP lower than 8, so that the communications for TP stay within a node, so that when you do forwards and backwards, you don't get stuck waiting for the all reduces or the reduced scatter and all gather in forwards and backwards. So now we've seen two axes of parallelisms. And before generalizing to the others, let's see what it means to combine them. So we've seen the data parallel, which shards data. Here we have data parallel size 3. And we've seen tensor parallelism, which shards the model into 2 dimensions. So what does it mean to combine these two? Well, the cool thing about the forms of parallelisms that we've seen, that they are orthogonal of each other. So if batch is sharded along the data axis, it's replicated. So it's replicated here along the model axis, and vice versa. If the model is sharded along the TP axis, it's replicated along the data axis. So this helps us like make a mesh of all the parallelisms. Now we've only seen 2, but later we can see 5, or there's even 6 or 7. Depends on how many parallelisms you want. And in the code, if you look at Torch Titan or Megatron or Nanotron, you're gonna see that at first they init the process group, so they init all the word size. Let's say you have 6 GPUs here. So you're gonna create your TP groups and your DP groups, and later you can just pick on which axis you want to do the communication operations. So for example, I want to all reduce, along the TP group. So I'm going to all reduce like this and all reduce like this along all the other axes. So this is the beauty of these parallelisms. We make sure that they are orthogonal of each other. And now we've gone through the first two big parallelisms. The last three, I'm going to go fast over them. So for PP, it's much easier than TP. So we have our layers like this, and instead of sharding them horizontally, I'm going to shard them vertically. So I'm going to put some layers on the first GPU, some layers on the second GPU. But we can see here that the problem is for GPU1, at the beginning, it doesn't have any activations. So it's just going to keep waiting for the first GPU. And for the first GPU, after after the forward goes through the first 4 layers, it just waits for the other GPU. So how can we solve this? And for pipeline parallelism, there is what we call PP schedules, pipeline parallelism schedulers. So the schedulers, they define how your GPUs are going to load the data, and they're going to communicate activations and gradients with the other ranks. So let's start with a simple assumption. Each GPU has one layer of your model, and we're going to start with the simplest scheduler, the all forward, all backward scheduler. So we're going to have the first batch, which is this one. So it starts at the first GPU, and then he sends the activations to the second GPU, and then third, and then fourth. And then I have another batch. So that's the GPUs don't wait. I'm going to schedule 8 batches. So all of them, they're going to do the forwards. And then they're going to do the backwards. So every time one GPU does the backward, it sends the gradients to the previous layer, etc. And I repeat this. So this is all forward, all backward. And I schedule multiple batches to minimize the idle time. So the idle time is this. And it's the biggest problem in pipeline parallelism. So the best way to solve it is to have more complex schedulers. So this is the one forward, one backward scheduler. And the name comes from the fact that if you prioritize backwards over forwards, you're going to have, at some point, like in the middle, you're going to have forward, backward. So they're interleaved, basically. Forward, backward, forward, backward. But we still didn't solve the pipeline bubble. This just helps with the memory a little bit. So the best way to solve it would be to start doing forwards from this side as well. And this is what DeepSeek has done in their dual pipe. So basically, if you have 8 devices, you're going to distribute the layers in a round-robin fashion. So the first layer, you're going to put it both on the first device and last device, so that both of them, they can start with data, etc. So there's a forward that's going like this, and there's a forward that's going like this, and then a backward like this, and then a backward like this, and you manage the overlap in the half. So as we said, it's easier said than done, because the implementation is very complex, and you need to keep track of the batches and the forwards and backwards, so that you send the correct activations and the correct gradients. So in general, the pros and cons. So the pros is that the communications are cheap. There's no all reduce, nothing to have a headache about. You just exchange the activations and the gradients. And the sharding is very efficient, because every GPU keeps track of just a shard of the model. It's model agnostic. I don't care about the nature of model, as long as I just have layers and I just send activations and gradients. And the cons is that I need to save activations for multiple micro batches, which is annoying. So for example, if in this case I had 8 backwards, in here they schedule 20 micro batches. So I need to save 20 times the activations for the different. So usually for PP and FSDP, since they rely on activations a lot, we offload the activations. So we use activation checkpointing, or now there is even CPU offloading. If you have a good GPU, you can offload the activations to the CPU, and then you just load them back when you need them. The other annoying thing is if you want to hide the PP bubble, you need an advanced pipeline scheduler like dual pipe, and the implementation is complex. It's very hard, and it's tough to add to the library. And third thing is you need multiple microbatches to hide PP bubble. So in a sense, this is like the DP issue, is that you need to scale your global batch size with the PP size. And the last two parallelisms, they are specific to two use cases. For example, for CP, the issue we want to solve is sequence parallelism. So once you scale your sequence length, the activations, they explode. So the question, even with TP, even with PP, the question is how can we amortize the memory cost when doing long context training? So what we've seen previously in data parallelism, when we have a batch, we can shard it along the batch dimension. But what we can do now is let's shard it along the sequence dimension. So it's analogous to data parallelism. But if I do that, and if I give different sequences to the GPUs, what about attention, right? Because when I do the forward, each GPU has only a part of the sequence. So how can I compute attention over my entire sequence? This is where ring attention comes from. And the idea is similar to online softmax that is used in flash attention. So you don't need to compute softmax out of the box. You can compute it in an online fashion. So each GPU, they compute softmax locally, and then they exchange K and V with the other GPUs. Then they update the softmax, etc. So this is the idea behind ring attention. So the problem with this, the small problem, is that we need to communicate K and V inside the attention block. So inside each attention block, which is a similar problem to TP. So it's also communication heavy. And for that, we can use send-receive operation for GPUs to send the other Ks and Vs. You can also use all-gather for that. So the pros is it's the only parallelism that efficiently partition large sequences memory. Sorry, and because the other parallelisms, they don't really shard the sequence. So if you have a big sequence, there's a problem. The cons is that it's communication heavy because in each attention block, you need to exchange Ks and Vs. And similar to DP, since each GPU sees different data, we need to all reduce the gradients. And it doesn't help much for short sequences. So really, it's really used if and only if you're doing long context training. And for the last one, EP, it's used for MOEs. And for MOEs, we don't have time to go really through them. But how can we parallelize them? So when you have your router and you want to route your tokens to different experts, you can just shard your experts across GPUs, right? So the question would be, what comms would I add so that I can do the routing? For routing, there is a switch transformer and top K version. So let's talk about top K, which is the more generic one. For this, let's take a look at all-to-all operation. So all-to-all, it's the most generic way of exchanging messages. So basically, you have, for example, 4 processes, 4 GPUs. Each one of them, they have 4 different messages. So all-to-all, what it does is just each process, it's gonna send their messages to the other 4. And each process, it's going to get messages from the other 4. So in a sense, all processes, they communicate with each other. It's like an n squared type of communication. It's the most complex one. And how does this apply in MOEs? So let's say each GPU has different experts. So when you're doing the routing, each GPU is going to have some tokens that need to be routed to the first GPU. So this is why all-to-all helps. So the first GPU here, which has the first experts, needs to get the tokens associated to it from the other GPUs. So how can we apply experts parallelism? First, we shard the experts across the GPUs, and only the experts. So experts parallelism is really only applied in MOE. It doesn't touch attention. And so to avoid duplicated work in attention, we need to shard data across GPUs, right? So EP is actually, it's not orthogonal to DP in this sense. So you also shard data across expert parallelism, and we need an all-to-all communication to route tokens to their respective experts, which is the operation that we call dispatch. And of course, we also need to combine them after the experts to retrieve the original sequences. So the problem and the biggest problem that you're going to face when scaling MOEs. So how do we know what all-to-all dispatch to use? So basically, in order to know how the tokens are routed, you need for the router to do to compute the scores, right? So the CPU needs to wait for the router to compute the expert scores. And this is annoying. Why? Because the CPU needs to wait here for the GPU to do the router calculation, what we call the dispatch preprocess. And the GPU needs to tell us what are the buffer sizes and what are the tokens per expert that we need. And to solve this, there is, for example, Deep EP by DeepSeek, and there is Hybrid EP by NVIDIA. And the only way to solve this is to use recent hardware so far, which has IBGDA and RDMA. So these allow us to, so they allocate specific SMs and specific memory to basically, whenever they calculate or they know which tokens to route to each GPU, they have already allocated the memory for that calculation. And this is a problem because, for example, if you have H100s or if you don't have InfiniBand network, you're stuck with this CPU-GPU sync. And this is why most labs who do MOE trainings, they have very slow trainings just because of this problem of hardware. And even like Deep EP that DeepSeek has open source, you're going to find out that it only works on IBGDA, which is InfiniBand. So the other labs have a hard time catching up with this. So in summary, expert parallelism is the only way to distribute MOEs efficiently, and it's communication heavy. It needs an all-to-all every MOE block, and since it has different data, it needs to all reduce gradients, and there is a CPU-GPU sync, which slows down your training very much to launch dispatch operation. So in summary, it is only to be used for MOE trainings, so the practical solution that people do to train with expert parallelism is to combine it with PP. And how do they do that? So we said that the dispatch and combine are slow. And if you remember for our one forward, one backward, we can overlap the forward and the backward. So what we do here is So we have two batches, which is the blue and the green here. So when we want to do this batch, which is for the blue batch, in parallel, we can do the backward for the other batch. And this is nice, right? Because so MLP here doesn't need dispatch, and we can do the dispatch here. And once this is done, we can do the dispatch for the other batch, etc. And this is already implemented in some libraries. For example, in Megatron, you can use these two flags. So in a nutshell, you can combine all 5 parallelisms, and you're going to have different communications in different steps of your training. And we've seen that CP and EP, so EP only apply to MOEs, and it only touches the MOE. And CP only touches self-attention here. And yeah, all parallelisms are orthogonal, so you can combine all 5 of them. And yeah, as a recap, we've seen the 5 parallelisms, and you can find a cheat sheet that we made in the ultra-scale playbook on how to make decisions following the number of GPUs you have. And finally, if you're more interested in the infra side of things, you can take a look at the small training playbook in the infra section. We've made a lot of benchmarks on how infra can handle these types of workload. And you can find more references in the 2 books mentioned, also the JAX scaling book for a TPU point of view. And if you're interested in these kind of things, contributions are very welcome. So Nanotron, Torch Titan, Megatron of them, and a lot of other libraries. So feel free to reach out if you want to contribute. And one last thing is, as we scale to thousands of GPUs, let's be mindful of their energy impact and use them responsibly. Thank you.
Okay. We'll also take any questions in person or over Zoom. Any in the room?
Yeah, thanks for the talk. It seems that for expert parallelism, you also have to have the tokens routed evenly across ranks, because if all of your tokens end up routed to one GPU, then everything else is idle. What are ways to fix this in practice?
That's what the load balancing tries to fix, right? So so depending on which approach, for example, DeepSeek, they initially introduced the load balancing loss. Oh, sorry. So the load balancing adds basically in the loss a factor that penalizes uneven distribution of tokens. And there's multiple ways to do it. There's the auxiliary loss free, where you just add a bias term when you compute the router, and it would automatically adjust the distribution so that it's even across GPUs.
Also have some on Slido. One is, do different parallelism strategies meaningfully affect scaling efficiency, model performance, or convergence? Or do they just enable reaching larger scales?
What's the first one? Scaling convergence?
Efficiency.
Convergence efficiency. Oh.
I think they meant like scaling loss.
Okay, so actually the different parallelisms do not change the forwards and backwards. So ideally, if everything is implemented correctly, it should have the same effect as if you had one GPU. So like the same scaling laws applies, and like you shouldn't find any difference in using PP over EP from like computation point of view.
Another is, how can we reduce GPU idle time during, say, RL training when CPU side checkpointing or environment data processing becomes sequential and a bottleneck?
Yeah. So for that, at least for text, you can allocate a lot of workers beforehand. So the PyTorch data loaders, they allow you to specify the number of workers that you can use, and they can pre-process the data before the training workload. So that should at least help alleviate the pre-processing so that it's done before you even go through the training iterations.
Any more in the room? Also, someone asked, do we have an automatic way to decide the best parallelism?
Yeah, there's been some papers for that. I think if you take a look at Jack's book, they've played with that, and like they let the TPU decide on what's the best parallelism. But it really depends on your specific, so model size, how many data you have, the global batch size, and the network you have. So the biggest factor in what we've said when you scale, of course, is the network bottleneck. So if you have, for example, let's say NVLink. So in GPUs, usually NVLink is either 4.8 or for the most recent one, 32 or even 72. So depending on that, you can even like use the more communication-heavy forms of parallelisms or the less communication-heavy ones. And for example, for TPUs, since they're in pods of 32, usually people, they allow themselves to use Tensor parallelism over the 32 pods. So yeah, it really depends on the hardware and the global batch size.
All right, thanks, guys. Thanks so much, Nouamane, for the amazing and insightful talk. So let's give it a hand again for our speaker.